All right, we just got back from our field trip to the elevator. And y'all got a chance to feel that change in weight. And again, you aren't actually changing weight, right? It's just this apparent weight. If you're in your textbook, we're over on page 102, where it talks about apparent weight. And they show you this lovely diagram of this young lady standing on a scale like that. And it's because the elevator is accelerating you, is why you feel this change in your weight. Because, and I get your question, 1 second. Here's the scale you're standing on, right? And here's you. Okay? Remember, there's two forces happening, right? Two things that are working on you. Gravity is pushing you down, and the scale is pushing you up. And those two things are equal, right? When we're standing still. Does that make sense? So when the elevator moves, it's going to change this calculus between these two things. Your question?
If the elevator did fast enough, would we hit our heads on the concrete?
Sure, right. If it suddenly shot downward, yeah. Yeah. The cables would be very slow. Yeah. There's no elevator that I know that would move that fast because it'd be dangerous, right? I mean, like, people would be injured if that happened.
Also, is it true, like, if the elevator does like start falling, if you jump right at the end before it crashes?
Well, what you're saying is you're moving downward with a certain velocity, and you're trying to jump upward to counteract that. You're still going to land.
Well, yeah.
But theoretically, you could take a little bit off of it, sure.
Yeah.
It all depends, I suppose, on how strong you are, how well you time your jump. Yeah. Yeah. I suppose it depends on how fast you were. I mean, that seems like an awful lot of velocity. I don't think you can jump fast enough to overcome terminal velocity. But yeah, if at a certain height, probably you could survive it. Yeah. Yeah. Okay, so let's go through the scenarios. Let's go through the scenarios. All right? So let's start when we're going downward. Okay? When I'm going downward, okay, the initial start, okay? So when we were going down, the initial dropping, did you feel less weight or did you feel more weight? We felt less, right? It's that brief moment of weightlessness, though you don't actually get all the way weightless, but less weight, less apparent weight. So the start is less, okay? How about at the end? The end, you felt more, right? Because you are, and again, I hope it makes sense to you. You're moving downward, and now the cable has to pull upward to slow you down. Does that make sense?
So it was a motor, and then it
Absolutely.
turns and then pulls.
Exactly. It's all just a simple pulley. It's very straightforward. Elevators are not super complicated. Yeah.
Like, in the movies, it's like all these little strings.
No, I'm sure there's cables that hold it, yeah. But, yeah.
All the extra cables.
Yeah. No, pretty straightforward. Let me ask you this. If you were standing on your scale in this elevator while it was moving between floors, constant velocity, no acceleration. You with me? Because that's how this elevator moves, right? You get going, and then it moves you very, very, very slow, and then it stops you. Right? That's how most elevators work. You aren't accelerating the whole time. Okay? So I'm talking about in this constant velocity time, what would your weight read on that scale? More, less, or the same as what you normally have? It'd be the same. Because we're back to this place where the two forces are equal. So this is at the start. It's less. During, it's equal. Right? During your ride down, it's equal. Right? Because, again, we have zero acceleration. All we have is just equal forces. The net force is zero. You're just simply moving, right? You're not accelerating. And at the bottom, when it slows you down, it pulls you upward, you're going to have more weight. Does that make sense? Now, if we flip this around, let me just cheat here and just clone this page. Where are you? Clone, thank you. Okay, let's change this, and now let's talk about what happens if you're not moving down. Let's talk about what happens if we're moving up. Gotta do my erasing here. Okay. So now instead of moving down, now we're moving up. Okay. So again, we're at the bottom of the elevator. We're moving upward. When the motion begins, what does your apparent weight look like? Heavier, because it's pulling the scale up into your feet, right? So it's going to read more weight. Your apparent weight will be larger. So start would be more. Okay? How about at the end? We get to the very top and it has to slow you down. Less, right? Less apparent weight. And then how about during? Again, no acceleration. You're just moving at a constant velocity upward. It would be the same. It would be the same. Are you with me that these are just opposites?
Yep. Well,
Does that make sense?
isn't it driving or during like the same?
It'll be the same. It'll be equal for both of them. Yes, definitely. Does that make sense, my friends? And it has to do with the fact that these accelerations are simply canceling each other out. So the problems I'm asking you to do tonight, or today, we've got about 10 minutes left of class, are numbers 20 and 21. And they're basically asking you to evaluate this motion. The example problem number 3, there on page 301, walks you through that math piece. But again, we're still using the same accelerations as we have in the past. Acceleration of gravity, and in this case, the acceleration of the elevator. So here's your assignment. Again, this is 4.2. It is on the page that has the number 104. And you are doing, please, numbers 20 and 21. Walk and wool.